Okay, let's take a look at number 1. Now in number 1, we see a right angle symbol. So that means that this angle is 90 degrees. And then we see a 45-degree angle here. And that automatically means that this other angle is 45 degrees. Remember that all the internal angles, so this is a big note, the internal angles of a Euclidean triangle, I'll explain what I mean there, of any Euclidean triangle sum to 180, or they add up to be 180 degrees. This can be pretty easily demonstrated by examining exactly what a triangle is. So it's a good idea to use the example of a rectangle, and then if you diagonally cut that rectangle like this, you have two triangles. See? Now here's the cool thing. So each of these angles in the rectangle is 90 degrees. Okay, so you can figure out the internal angles of a rectangle. You have 90 plus 90 plus 90 plus 90. Well, that's 90 times 4. Okay, and that's going to be 360 degrees. Well, okay, fine. So now if I cut that rectangle in half diagonally, what have I got? I have now cut the angles here down, and so I don't necessarily know these angles. I can, that's 26 degrees, right? So this is 26 degrees. This is still 90 degrees. And then in order to find this missing angle here, I would just need to take 90 plus 26 and then subtract that from 180. And that would make this angle 64 degrees. And so all a triangle is half a rectangle. And I hope that helps understand how the internal angles of any triangle have to add up to be 180. Since the internal angles of the larger rectangle added up to be 360. Okay? So that's a little cool stuff about that triangle, internal angles thing. Okay, so now looking at this problem, we see that, yeah, we're given 45 degrees, and then we have one side length. Remember what we were doing before, which was we were drawing, saying, well, okay, the side length opposite the 45 degree angle here is going to be equal to the side length opposite the other 45 degree angle. It's going to be equal to it. So if this is 20, then y also equals 20. Right? So that's the thought process. You can just say that. You can claim it. So we already know one of the answers is going to be 20, and that's going to be what y is. Okay, so y equals 20. But what about x? All right. Now there's an easy way to do this, and there's a harder way to do it. We'll start off with an easy way to do this. Okay, so remember the relationship that we showed in the over here. Same, square root 2. No, 1, 1, square root 2. So the question you should be asking yourself is, well, we have the same thing here. We have same, blank for the hypotenuse. X is the hypotenuse. Well, what happened to 1 to turn it into 20? Remember I said it was proportional. So 1 got magnified 20 times, okay? And so it was scaled 20 times, so that's 1 times 20, okay? Over here, the same thing happened. You had 20 times 1 gave you a side length of 20. So if the multiplier was 20, then x should equal 20 square root 2. Since if the side lengths opposite the 45-degree angles had been 1, then the hypotenuse would be square root 2. But the side lengths aren't 1, they're 20. But that just scales the whole triangle up. So if you know 2 of the side lengths, but that doesn't include the hypotenuse, then you can just jump to the hypotenuse by multiplying it by the scale factor of whatever it is. In this case, it's 20. So x is 20 square root 2. Now, you're supposed to be showing your work on this. So the way that I would show my work on this is I would assume that I didn't know that. Assume I didn't know this little trick, right? You think of this as like the scale trick. Okay. Then the way that you would actually figure it out is having established, maybe drawing these lines like this. That'll show the person looking at it that you knew those relationships. Then you could test using the Pythagorean theorem. So remember the Pythagorean theorem, maybe if I could spell it correctly. The Pythagorean theorem, I know most people are going to say a squared plus b squared equals c squared. Okay, like this. That's fine for what you've known so far, but what is a squared, what is b squared, and what is c squared, and why do we care? You're like, short answer is, I don't care. Like, okay. But these are the we'll call them the sum of the squares of the two shorter sides of a triangle. Okay, the sum of the squares. You see that? It's the sum of the squares of the two shorter sides of a triangle, should say right triangle here, are equal to the square of the longest side. Okay, you could think of this as the square of the longest side. And that we have a special name for that side, and that is the hypotenuse. So the sum of the squares of the two shorter sides equals the square of the longest side. Okay, that's the Pythagorean theorem in a way that is actually useful for us here. Shrink that guy down for a second. Stick him up here. Okay, so for this problem, if we were doing a squared plus b squared equals c squared, I would prefer to write it like this, if that's okay. C squared equals a squared plus b squared. So there's a reflective property of equality that says I can do that. Nothing changed. In order to get c all by itself, we have to take the square root. In order to like unsquare something, you take the square root of both sides. Okay, so that's how you unsquare something. It's like square root say square rooting is how you unsquare okay. All right. Now we have numbers here. So we're presuming we don't know what c is, like the hypotenuse, but we know that we have, so when you unsquare something, you just get that thing. So this is just c now. That's going to be equal to the square root of, and now we can substitute, we were given x and y to be 20, or we found y to be 20, we were given x to be 20, so we have 20 squared plus 20 squared. Okay, 20 squared is just 20 times 20, and 20 times 20 is 400, so we have c equal to the square root of 400 plus 400. Okay, so that's the square root of 800. But if you write down the square root of 800, you will get it wrong. Remember, we thought it was 20 square root 2. So the question is, how do we go from the square root of 800 to getting that to be 20 square root 2? Are those two things even equivalent? Okay. Well, here's how you do it. You have to take the number underneath the radical symbol. So this symbol is called a radical symbol. And you have to break it down. You have to prime factor it. I want to find like a color for prime factoring. Maybe I'll use this color here. No, let's use like blue. Okay. So we have to prime factor, and we have to know our prime numbers in order to prime factor. So the first few primes are going to be 2, 3, 5, 7, 11, and then it goes up 13, 17, like that. But you probably only need the first 3 or 4, 11 is less common. But primes are any number that can only be divided by themselves and 1. And the only even prime number is 2. 1 is not a prime number, but it doesn't matter if you forget that because it just is kind of irrelevant for these problems. So when I say break it down, here's what I mean. Here's how to prime factor a number. Okay, let's prime factor 800. Well, 800 is even, so the first prime is going to be 2. And then we talk about the other number that goes with the 2 is called a cofactor. So the cofactor isn't as important for what we're doing here. The cofactor would be 400 for the prime factor of 2. And then we're going to break that down further. 400 is still even, so the prime factor again would be 2, the smallest prime factor, and then that cofactor would be 200. So now break it down again. 200 is still even, so the prime factor will again be 2, and that cofactor will be 100. Let's break it down further because we can still keep going. Well, the smallest prime factor, since 100 is even, would be 2, and its cofactor would be 50. Okay, there's only 2 more steps. So here you break 50 down and say, well, okay, it's an even number. Prime factor is going to be 2. All even numbers greater than 2, the prime factor will be 2, and the cofactor here will be 25. And now we finally have a non-even. 25 is an odd number, and we know 5 times 5 is 25, so there are 2 prime factors. Both the factor and the cofactor are identical, and they're both 5, and 5 is prime. So you see we used this prime number and this prime number. So now what I like to do is circle those prime numbers. How many 2's are there? 1, 2, 3, 4, 5 2's, and then 2 5's. Okay, so those are your numbers. And what this means when you prime factor like this is it means that 800 is actually equal to the product of the primes. What do I mean by product of primes? I mean 800 is equal to 2 times 2 times 2 times 2 times 2 times 5 times 5. Okay, so that's pretty cool. Yeah. So now that you know that, you can take what you just drew, these, and you can replace the 800 with those prime factors underneath the radical symbol. Okay, so let's say, go back to our work here and say, if C equals the square root of 800, then C equals the square root of, and then you can put in all these prime factors. Remember the product of the primes. So you can put in 2 times 2 times 2 times 2 times 2. There were 5 of them. Times 5 times 5. Okay. Now, here's a cool trick. All right, so let's highlight pairs of 2's. And here's one pair of 2's, 2 pairs of 2's, and then that 2's all by himself. And then we've got one pair of 5's. And so the only thing left over inside that doesn't have a pair is that one solitary 2. Now here's the really cool thing. So with primes like this, and sorry, with pairs of numbers like this inside of the radical, you can group these pairs like this, and you can almost do like a reverse distribution property thing, which is a really terrible way of explaining it. But basically, I should probably just show this step here. So 2 times 2 is the same thing as 2 squared. Okay, 2 squared times 2 squared. And then you've got that 2 all by itself, but I'm going to just reorder these two. I'm going to flip the location of these two here and say 5 squared times 2. So now C can be written like this. Okay? Well, there's a product of roots that says if you have the square root of a square, you can break that up like this. And, well, you have the square root of products inside, you can break the root up. So it's perfectly legal to write this like this. C is equal to the square root of 2 squared times the square root of 2 squared. So you see I'm making a bunch of little square roots. Times the square root of 5 squared times the square root of 2. How interesting that we have a square root of 2 hanging out there at the end. I wonder if that's like relevant to this 45, 45, 90 triangle. Hint, it is. Okay. All right, so now here's a cool thing. The square root of a square is just that number. So if I actually take the square root of 2 squared, the answer will be 2. The square root of 2 squared, 2. The square root of 5 squared, 5. Now here I don't have a square inside, so I just have to leave this guy. Square root 2 has to stay square root 2. But except for that one at the end, you're going to get a 2 by itself, a 2 by itself, and a 5 by itself. And they're still going to be multiplied together. So this is now C equals just 2 times just 2 times just 5 times square root 2. Okay. Well, let's simplify. So 2 times 2, that's 4 times 5. Okay. So now C equals 4 times 5 times square root 2. And 4 times 5 is 20. So the final answer is 20 square root 2. And that is deserving of a red box of correctness. I guess it's going to be, well, there we go, red box of correctness. Because if you go back and look, that's precisely what we thought it would be. So, final answers, you have x equals 20 square root 2. And y equals 20. And that is your answer to that question. All right.